Hello and welcome to episode 24 of Diabetics for Diabetics Radio. I am your host, Bowie Madison. We're here talking about iron, beta cells, and the liver, the unknown health triad at the root of mitochondrial health, energy metabolism, and diabetes. We're going to dive into kind of an unknown Bermuda Triangle of sorts in cellular metabolism that plays such an honestly well-documented role in creating energy. And in our world of autoimmune conditions and chronic inflammatory conditions, all born of poor cellular respiration, poor mitochondrial health, we've kind of lost sight of how these three interact and how in addressing these conditions, we aren't really paying attention to these three things. So we're going to start to connect the dots in how these things interact. Now, if we have not met, my name's Bowie. I've had type 1 diabetes for over 21 years. I have spent the past 2 of those diving into the research, connecting the unspoken dots in the literature and textbooks regarding cell physiology, mineral balances, all of the things that are not being shared in your standard endocrinologist visit. So I've got this podcast, I've got a TikTok channel, short form content, these longer, 30 plus minute podcasts, all looking to spread more information on what we know about inflammatory cascades within the body relating specifically to iron overload, which is something that I've been focusing on in my research and practice in managing my own symptoms. So let's go ahead and start to talk about it. Okay, so what is this triad that I'm talking about here? So we've got our liver in the upper left, we've got our pancreas in the upper right, and this lovely iron molecule, okay, the mineral in our diets. So much connection between all three of these, right? And by the end of this podcast, we're going to know enough about all three of these to know how they do what they do, how they interact with one another, and in a dysfunctional state, who we get to point the finger at for what's going wrong, okay? So we have to know the players, right? And I've covered plenty on what the liver does. This is just a kind of a quick overview to make sure that we have a basic understanding of the liver's role as it specifically relates to managing iron in the body. And then we'll kind of connect the dots with iron itself as a molecule and its role in the body as well as the pancreas. So the liver. It is the site, it is the management, the throughway of iron in the body, right? So when most people think of iron, they think of its role in hemoglobin, right? It is the major oxygen carrier on red blood cells that delivers oxygen throughout the body, right? So you can see there 80% of iron in the body is connected to hemoglobin delivering oxygen, okay? That being said, the liver doesn't just filter the red blood cells, right? It is storing iron, right? So it is taking the iron off of those recycled red blood cells and it is distributing it throughout the body where it is needed. Now, where does it go? Most of it is going back to the bone marrow where red blood cells are being made so that iron can bind to those new red blood cells to kind of continue that life cycle all over again. Our body is incredibly efficient at recycling iron. About 95% of the iron in our body is being reused and reused over and over again, with only 5% being excreted via feces, sweat, urine, what have you. But very efficient system, and all of it runs through the liver. All right. So for the iron that's not being sent to the bone marrow to be sent and reattach to the red blood cells. It can be sent to cells where it is being used for cellular respiration, and we'll talk later on about how iron is used in the electron transport chain to create energy in the cell, in the mitochondria. So it's either sent to the cell, or it can be sent to the GI tract, or the kidneys, or the skin, or the lungs, to be honest, to be excreted and removed, right? And like I said, our body's incredibly efficient with iron. And because it's so efficient, we really only have the capability to get rid of so much. So we're able to excrete anywhere from 1 to 2 milligrams per day of iron. Now, for anything that's not being used actively or excreted because it's run its course and it's gone, that remains in the liver for storage, right? So the liver is ground zero for anything to do with iron. It's where things are recycled. It's where things are repurposed. It's where things are stored. So if you want to know about iron status, or if there's any sort of dysregulation in terms of iron, you need to know what's going on at the liver, because that's where things are happening. And when it comes to mapping out dysfunction specifically, you have to know what else is connected to the liver. And because the liver is so multifaceted in what it's able to do, it is very well connected in other organ systems, okay? So the liver secretes hormones. Therefore, it's connected in the endocrine system, okay? So it has a direct line to the pancreas. It has a direct line to the rest of the endocrine system. So everywhere from the brain and the pituitary, the thymus, the thyroid, all the way down to your gonads, the testes and the ovaries, okay? So it's distributing hormones via the endocrine system, okay? It secretes bile. It stores fat-soluble vitamins and other minerals. I believe magnesium's in there as well. So it has a role in the digestive system and digesting fats and processing vitamins and minerals, right? So that, map out the digestive system. That's your esophagus, your stomach, your intestines, your colon, your kidneys, the excretory system, okay? That's the kidneys again. It has so many ties to so many systems. It is so deeply rooted in so many important bodily functions that when you are dealing with liver dysfunction, it leaves such a huge crater in its wake, right? Because liver dysfunction, if the liver is not able to do what it needs to do in any way, it is upsetting the endocrine system. It's upsetting the digestive system, and it's upsetting the excretory system. Okay, so you've got these neat little pictures here. We've got the pancreas here connected to the small intestine, the mouth of the small intestine there. The pancreas is also a digestive organ that has a role in breaking down food as well. So it's the liver in all of that would be right above and right over the pancreas, with the gallbladder kind of hanging off the side there. So all next door neighbors. You know, if you're thinking of all these organs, they are all very close together. And then expanding on the results of liver dysfunction downstream within all of those symptoms. You think of all the organs and tissues that are involved, like I just mentioned. What are the things going on in those systems that are affected by our autoimmune conditions, by our chronic inflammatory conditions, right? People having their gallbladder taken out, PCOS, infertility, Hashimoto's and the thyroid, diabetes, and fibrotic buildup in beta cells, a loss of beta cell mass, a loss of insulin sensitivity, blocked bile ducts. With the fibrotic gallbladders, all of these things are so closely related to the liver. And all we're doing right now is looking at each of these symptoms in isolation without understanding their common connection upstream at the liver. So food for thought. We'll connect the dots. All right. So next player in that triad is iron itself, the iron molecule. Okay. So we know where it's being stored. It's, the liver is kind of the main site where it's being handled because it is an incredibly important mineral. Okay. So it is a proton donor and acceptor. That is what makes it such a great oxygen carrier on hemoglobin. It binds readily with oxygen because oxygen is equally as reactive. So a match made in heaven there. If it's not dealing with oxygen, it is being a catalyst in the electron transport chain, donating and accepting electrons in order for mitochondria to create energy. Okay, so no matter where iron goes, whether it's on hemoglobin with oxygen or it's in the electron transport chain creating energy, it is so incredibly reactive. It has a high potential for energy exchange. Now, when you think of that and you see that reactivity of iron, it has to get you curious about, okay, it's like an electric charge. You have to make sure you're handling this thing with gloves so that you're not getting electrocuted, right? And when you look at the body's transport system for iron and safety mechanisms built around iron, you understand that the body knows how reactive iron is. I'm tempted to say dangerous because iron is dangerous if it is used out of context. So we'll see that the body has built-in defense mechanisms to prevent iron going places where it is not supposed to, because as we'll learn, the consequences are dire. So this is from a 2018 paper, or 2016 paper, sorry, going over the role that iron has in mitochondria, right? So this paper is a little bit of a meta-analysis, kind of going over some of the existing questions in how iron is being used in the mitochondria. This particular paper was very specific in the chemistry of the outer mitochondrial membrane, the inner mitochondrial membrane. For the purposes of this podcast, we're not going to talk about specific electrons being donated, the pyruvates and the citric acid cycle going on in each mitochondria. Rest assured that iron is a vital component in the effective transfer of energy going on in every mitochondria. Okay, so as you can see here, iron is a key player in many important cellular processes, including energy metabolism, cellular respiration, and DNA synthesis. Mitochondria are major hubs of iron utilization and accumulation, and iron in the mitochondria functions as a cofactor in iron-sulfur cluster-containing proteins, heme-containing proteins, and iron-ion-containing proteins. So, needless to say, iron is a permanent resident in mitochondria. VIP, very important, much needed, and always being used to some degree in creating energy. And this is just a brief illustration, like your kind of classic textbook demonstration of the electron transport chain. I'll give you a second to look it over, but it's not too hard to find iron, right? There it is, right? It's so readily accepting and donating electrons there. So you see that going through redox reactions, complex 1, complex 2, and complex 3 of the electron transport chain. So it's multiple roles, and this is all going on within the mitochondria of your cells. So let's go on to the last player here, the beta cells. So this is one of, I want to say 6, but 4 main cell types within the pancreas, okay? It's responsible for secreting both insulin and amylin. For the purposes of this podcast, we're going to talk mostly about its role in secreting insulin. Insulin is secreted as glucose is absorbed by the small intestine. So we ingest our food that has carbs in it. Once it hits our small intestine, it's going to affect our blood sugar. And when our blood sugar starts to raise, right, because our blood is taking that sugar and getting ready to distribute it throughout the body, our pancreas releases insulin into the bloodstream that acts as kind of like a key, for a lock and key to get the glucose into the cell. Without insulin, the glucose remains in the blood and is unable to get into the cell to be used for energy, right? Now, that last point there, it's necessary for efficient cellular uptake of glucose. Now, there are alternative ways for glucose to get into the cell, but they are incredibly inefficient, and insulin is the preferred hormone for getting that done. Okay, now not a lot of diabetics know that, honestly. They think, well, if you unless it's insulin, glucose isn't getting into the cell, and that's not necessarily true. But to remain healthy and to effectively regulate your blood sugar to a healthy level, you're going to need insulin for what you're eating. Now, given what we know about the role of all 3 of those players, the liver, the beta cells, and iron molecules, what similarities can we kind of connect all of these 3? Okay, so this is what I came up with when I was looking at the role of the liver. I was interested in iron overload and kind of all of the inflammatory chaos that causes. So the liver is responsible for managing iron, right? It's repurposing it, recycling it, it's storing it. If you want to know where liver is going, or if you want to know where iron is going, check the liver. Iron itself, the molecule, the mineral, is important in proper energy creation. Our mitochondria are iron rich because they need it in creating cellular energy. Insulin has a similarly important role in facilitating glucose uptake in order to allow for energy creation. And that's where I started to connect the dots, because, okay, the liver determines the availability of iron, which is very important in cellular energy. The pancreas determines the availability of insulin, which makes glucose available for cellular energy. Okay, so 2 very important factors in mitochondrial health, in the cell's ability to create energy. What could they possibly have in common, right? What are some ways that we can draw connections here that can play off of each other in the event that one of these is not able to do their job? So I'm looking for a deeper relationship. Now, shouldn't beta cells have a unique relationship with iron, right? Because beta cells are like the step number 1 in making energy possible. They're the ones opening the door for glucose to get into the cell. Now, once glucose gets into the cell, iron is one of the main dogs in the mitochondria, making glucose utilization possible for the cell to use the ATP from it. So I'm thinking there has to be some line of communication or some relationship between beta cells and iron utilization, because when a cell senses that insulin is here, that means it has to have iron at the ready for the newly delivered glucose to create energy, right? And okay, so you've got that unique relationship between the beta cells and the glucose. Well, the liver is what is ultimately determining the availability and the circulation of iron. So as someone with diabetes, I'm wondering, okay, so something happened at my beta cells where insulin is no longer being secreted. Structurally, genetically, the cells do not make insulin, right? There's something going on there where iron isn't able, or glucose isn't able to enter the cells. Now, this is just another demonstration of that trifecta that we talked about in the beginning. So if you know this podcast at all, we've talked a lot about how iron can influence the health of cells, especially in states of excess. Iron is very dangerous. Iron is very reactive when it is not properly bound. So, in a perfect triad here, iron is properly recycling and transporting via the liver. Liver is taking in those red blood cells, repurposing all of that iron. It stores what it needs to, in case of an emergency, and distributing what we eat as is needed. The pancreas senses glucose in the blood, releases insulin, making that glucose available to the cell for metabolism. The iron already in the mitochondria, distributed from the liver, is there to catalyze cellular respiration. Without it, mitochondria do not perform correctly. Now, we know that the liver and the pancreas have a connection in a healthy system, right? Regardless of what the dysfunction is, both in a healthy state, right? So that second dot here, glucagon secreted by the pancreas is what signals glycogen released by the liver. So alpha cells in the pancreas release glucagon. Glucagon goes to the liver and tells the liver to release glycogen to be the up to insulin's down, right? Every diabetic is familiar with the word glucagon. So we know that they are able to communicate. They need to communicate in a healthy system, right? Because those are the two main organs regulating blood sugar. And in a state of dysfunction, specifically iron overload, initially in the clinical states of hemochromatosis and thalassemia, in which the body is not able to properly process iron, the pancreas is a site where iron starts to accumulate in a way that is not healthy, right? So people with hemochromatosis are 50%, 50% of people who get hemochromatosis are going to develop diabetes. People with hemochromatosis have fibrotic tissue buildup in their pancreas. They are also insulin resistant, hence the development of diabetes. So we know that a dysfunctional liver that is unable to effectively manage its iron load, it has inadvertently affected the health of the pancreas, specifically the beta cells. So my question is, when the pancreas becomes loaded with iron after that liver is dysfunctional and cannot handle the iron load, why is it that beta cells are preferentially affected to any of the other beta cell types? There are alpha cells, there are beta cells, there are delta cells, there are gamma cells. Why is it that the beta cells are the ones being targeted? So you have to ask yourself, okay, well, we know about, they both have a tie to cellular energy, right? Insulin helps the cell use glucose. Iron helps the cell break glucose down. What is it? There's something within probably the beta cells that would make them a designated target for iron overload. What could that be? So let's just read this last point here. Beta cells regulate energy use and thus have a unique tie to other components of proper energy usage, right? So beta cells have some sort of role in iron mobilization, because when glucose comes into the body via our food, insulin is telling the cell, hey, glucose incoming. Mobilize that iron so it can help catalyze the electron transport chain. And so here we go. This is a paper from 2008 talking about how pancreatic beta cells were found to express hepcidin, which is an iron uptake regulatory peptide. Now, prior to this paper, it was believed that hepcidin was only found in the liver. Hepcidin's nickname is the master iron regulator. Okay, we'll talk a little bit more about what hepcidin actually does, but because of its role in iron homeostasis and the liver's role in iron homeostasis, it was thought that hepcidin was reserved just for the liver. Sure enough, they found hepcidin in beta cells, not alpha cells, not delta cells, not gamma cells, just beta cells. Okay, so the master iron regulator, hepcidin, in beta cells and no other cell type in the pancreas. So within this paper, it was found that beta cells are the only pancreatic cell type with hepcidin. And with higher levels of inflammation, whether acute or chronic, the levels of hepcidin are upregulated. So when inflammation is present, cells with hepcidin create more hepcidin. When more hepcidin is created, serum iron levels decrease. Okay, so hepcidin is like a warden. It is what decides whether or not iron goes out of the cell or into the cell. The more hepcidin there is, the more iron stays in the cell. So that's why when there's inflammation and more hepcidin is pulling iron out of the serum into the cell. So therefore, increased hepcidin correlates with the pathophysiology of anemia, right? More hepcidin, less iron in the serum, right? So if you were to go get a blood test for serum ferritin with high levels of inflammation and high levels of hepcidin, your tests are going to come back saying that you have low serum ferritin. And you'd probably get diagnosed with anemia. But the iron itself didn't go anywhere. It's not in the serum, it's just in the cell now. So this increase in inflammation causes a reduction in the serum iron levels, and iron isn't able to leave the cell. Now we start to connect the dots because we know what happens when iron is locked in a cell that does not have the capabilities to manage it. So the liver becomes overloaded with iron. Its storage cells are filled to the brim, and it doesn't have any place else to put it. Iron infiltrates other cells, right? The GI tract, the endocrine system, the excretory system. Iron in cells that do not have the means to manage it becomes very reactive. It causes an inflammatory response. That inflammatory response causes cells with hepcidin to upregulate hepcidin to prevent serum iron from being like gas on the flame, right? Because the body knows how reactive iron is in a state of inflammation. So it upregulates hepcidin, retains all that iron in the cell. Beta cells, having hepcidin, are now retaining more iron than usual. When you retain more iron than usual, you are setting yourself up for more inflammation. That is why beta cells are an inadvertent victim of iron overload, more so than alpha cells, more so than delta and gamma cells, right? That explains why beta cells are specifically targeted in a state of iron overload. Okay, so that is the long and short of it. That is it. It's hepcidin. It's beta cells and their relationship with iron because of their common connection to energy production, that the beta cells have the tools to regulate to some degree iron levels, right? Because they're both dealing with energy. But that backfires in a state of iron overload, because iron, now being the source of inflammation, triggers a safety mechanism that pulls iron out of the serum into the cell typically to prevent inflammation from happening elsewhere. But in this case, it's actually making things worse because iron is the source of inflammation. So now we've got too much iron in a cell with a safety mechanism that's trained to pull more iron into the cell. And then you've got an implosion. So these beta cells are now retaining even more iron, more oxidation, more free radicals, more inflammation, and thus they're being killed off. Okay, so that explains the love triangle. I'm being facetious here because it is not lovely, but that is why I am so enthralled with this iron overload mechanism, because it's all explained here. I mean, that's why beta cells and no other cell type within the pancreas are being so affected by our inflammatory responses, and because the liver is so well connected in the endocrine and the excretory system as well. I mean, iron is not just being distributed to the beta cells, it's being distributed in the gallbladder. That's why people are having their gallbladders removed. It's being distributed through the kidneys. It's being distributed to the thyroid, the pituitary, into the brain, I'm sure. So wherever there's inflammation, we have to be looking for iron. And wherever there's inflammation caused by iron, we have to look back at the health of the liver and why why it is so full of iron. Okay. So that's what this podcast, I'm going to end it here because I could go into a whole nother podcast about the management of iron, which I have talked about before. But this is how iron negatively affects beta cells. This is how beta cells are equipped. They've kind of got a smoking gun of sorts in this inflammatory cascade, explaining why they are being targeted over any other cell type within the pancreas. And so it goes. Okay. So that's it for episode 24. The liver, iron, and beta cell love triangle. My name is Bowie Madison. Thank you so much for being here. If you have any questions, do not hesitate to leave a comment. Follow me on TikTok at Bowie_Madison and subscribe here for more weekly content regarding diabetes, iron overload, and any sort of autoimmune condition resulting. All right. So thank you so much for being here. I really appreciate it and enjoy.